The function has a limit L at an input A if f of x gets closer and closer to L as x moves closer and closer to A. There are two types of limits when studying continuity: right-hand limits and left-hand limits. Here's an example. When studying the limit 1 over x squared when x goes to 0, we discover there's an indetermination. So we try and find the lateral limit. So we plug in the function 0.111 and minus 0.111. And in both cases, the limit gives us infinite values. So here's the graph that is the result. When studying the continuity of a function in x equals to a, there's a condition that must be achieved. That is, when the limit of x of a right hand equals the limit of x of a left hand equals f of a.
Different types of discontinuities. Here we can see three different types of discontinuity. The first one, jump discontinuities. The second one, infinity discontinuities. And the third one, removable discontinuities. First of all, we're going to study jump discontinuities. For example, when the graph of f of x goes below, shows a function that is discontinuous at x equals to a. This is the example. In this graph, you can easily see that the limit of f of x when x goes to a from the left side is equals to L, and the limit of f of x when x goes to a from the right side is equal to m. The function is approaching different values depending on the direction of x is coming from. The next discontinuity is infinity. The graph below shows a function that is discontinuous at x equals to a. The arrows on the function indicate it will grow infinitely large as x approaches a. Since the function doesn't approach a particular finite value, the limit does not exist. This is an infinitive discontinuity. The last one, the removable discontinuities. In the graph below, there is a hole in the function at x equal to a. These holes are called removable discontinuities. Notice that the graph, even though there are holes at x equal to a, the limit value at x equal to a exists.
Infinite limits and limits at infinity, asymptotes. A function can behave in a peculiar way. We can distinguish two types. There's the infinite limit, when a function f of x goes to plus or minus infinity, when x approaches to a. Therefore, there's a vertical asymptote. There's the infinite in infinity, when a function f of x goes to a, which is constant, or behaves like a straight line, when x goes to plus minus infinity. Therefore, there's a horizontal and oblique asymptote. How to find asymptotes? First, how to find vertical asymptotes. You have to first do the limit of x when it goes to a. So f of x equals plus or minus infinity. Then there's the horizontal asymptote. That is when the limit of x goes to plus or minus infinity. So f of x equals a. Then y equals a. That is the horizontal asymptote. And then at last there's the oblique asymptote. That you have to do 3 steps to get the oblique asymptote. The first step is the limit of x when it goes to plus or minus infinity. So f of x equals infinity. Then there's the second step, that the limit of x goes to plus or minus infinity of f of x divided by x. And that gives you a. A is the slope of the curve of the oblique asymptote. And for last, there's the limit of x when it goes to plus or minus infinity. F of x minus mx, m is the slope, equals b, and b is what we call the y equals mx plus c. C will be the b, that is the last step to find the oblique asymptote. Example of an asymptote. The first one, the limit of x when it goes to infinity of 1 plus 2e to the power of x divided by 1 minus e to the power of x equals limit of x when it goes to infinity of 1 divided by e to the power of x plus 2 divided by 1 divided by e to the power of x minus 1 equals 0 plus 2 divided by 0 minus 1, that equals minus 2. We know that e to the power of x gets close to 0 as x to the minus infinity. So, limit of x to the minus infinity of 1 plus 2 times e to the power of x divided by 1 minus e to the power of x equals 1 plus 0, 1 minus 0, that equals 1. So the lines y equals 2 and y equals 1 are horizontal asymptotes. To find the vertical asymptote, we notice that the denominator is 0 when x equals 0, and so when x goes to the left hand of 0, the denominator is positive, close to 0, and the numerator is positive, close to 3. So the limit of x when it goes to the left hand of 0 is 1 plus 2 times c to the power of x divided by 1 minus c to the power of x equals infinity, and the line x equals 0 is a vertical asymptote. Before, when finding the horizontal asymptote, we looked at the limits at infinity. We know that c to the power of x gets larger and larger as x goes to plus infinity. So that's why we have studied at first place the limit of x when it goes to infinity.
Now we're going to study the limits with the parameter a. So limit of x when infinite is positive is root of x squared plus ax plus 1 minus x, which equals to limit of x when infinite is positive, which is root of x squared plus ax plus 1 minus x times root of x squared plus ax plus 1 plus x divided by the root of x squared plus ax plus 1 plus ax, which equals to the limit of x when infinite is positive, which is x squared plus ax plus 1 minus x squared divided by the root of x squared plus ax plus 1 plus x, which is the limit of x when infinite is positive, which is ax plus 1 divided by the root of x squared plus ax plus 1 plus x. Then the next step would be to divide the numerator and the denominator by x. So it equals limit of x, which is of x plus infinite, which is a plus 1 divided by x divided by the root of 1 plus a divided by x plus 1 divided by x squared plus 1, which equals a plus 0 divided by the root of 1 plus 0 plus 0 plus 1, which equals a divided by 1 plus 1, which is a divided by 2. So the question forces us that the answer needs to be 2, which is a divided by 2, which is 2, a equals 4.